Hello all my dear students, I'm Suhasini. Welcome back to my channel Learn with Suhasini Shinde. In the very last class we have discussed about the potential energy of a system which has two charges initially. Then we had put three charges into it, right? The very next derivation was finding out what was the potential energy when the system itself consists of electric field, right? Now the very next derivation in this particular class will be finding out what is the electrostatic potential energy of in an electric dipole when it is placed in electric field. Okay, now these are electric field lines and we place a dipole into it. Dipole is nothing but two equal and opposite charges placed at some particular point with a distance of a very small distance of 2a between them, right? Now this forms a dipole. The dipole is kept into electric field. This is electric field, right? We have to find out what is the electrostatic potential energy on this dipole when kept in this electric field, right? Now plus q and minus q forms a dipole with a small distance 2a, right? And whenever I say dipole, there exists a dipole moment. What do you mean by dipole moment? Dipole moment gives a strength of the electric dipole, right? Now this dipole moment is making an angle theta with the electric field, right? Now this can be represented as P, right? Now whenever you have an electric dipole placed in some electric field, both the ends will be exerting some force on it, right? The force Q into E will be exerted in this direction. Why? Because it is a positive charge. In positive charge, right? Positive charge electric field lines are always aligned in a direction of electric field, and the another force is exerted on minus Q in the opposite direction of the electric field, that is minus QE. Right? The electric field lines are always in the direction of the positive charges and it is opposite to the direction of the negative charges, right? Now this is a dipole which is placed at this particular electric field with a distance of 2a, and this dipole moment which gives the strength of the dipole is making an angle theta with the electric field, right? Now at the ends of the dipole it exerts some force, right? Force of QE, right? The two forces that are acting on the opposite ends will create or exert a torque in this particular dipole, and hence the dipole starts rotating or moving into this electric field, right? Now what is the torque that is given? Torque is being explained with torque will be equal to force into perpendicular distance between them, right? Now what is force? Force is nothing but QE. What was the force that is acting on this Q? That is QE. What is the force that is acting on this minus Q? That is minus QE, right? Now the product of the force and the perpendicular distance between them will give rise to the torque. Now this torque will make or rotate the dipole into the electric field, right? Now, how do you find out what is the distance? Now you just drop down these lines so that we get a distance. Now this is the perpendicular distance, right? If at all it is a point A, if it is B and this is C, right? BC forms a perpendicular distance between the two dipole, that is the dipoles, right? So how do you find what is this B? It is opposite. How can we find this particular distance? In this formula you get this BC, that is sine theta will be equal to BC by AB, right? So how do you write? Okay, what is the sine theta? Sine theta can be defined as BC by AB, right? BC by AB. What distance we wanted? What was the perpendicular distance? It is BC. So you express this equation in terms of BC. BC will be equal to AB sine theta. What is AB? AB has a value of 2A. So it is BC is equal to 2A sine theta, right? What was force? Force on any one charge, right? It can be positive Q or it can be negative Q. So the torque will be given as, what is force? It was Q into E, right? Perpendicular distance is 2A sine theta, right? From this equation, if you could notice, you have a dipole moment equation into it. That is, what was dipole moment? It is a product of the distance between the charge, right? 2a into q. 2a, this q can be directly substituted with the dipole moment now. So how do you write? Torque is equal to Pe sine theta, right? Now this is the torque value with which this dipole starts moving into this particular electric field, right? If at all you want to hold this dipole in this particular direction, now see, do not confuse, right? Listen carefully. Now this is the torque value with which this dipole starts rotating, right? In which direction it rotates? Now this is here, the force is here and the force is in the negative opposite direction. It starts rotating in this direction and this move here. Now what direction this is moving? It is moving in clockwise direction. With what torque it is moving? With what value of torque this dipole is moving, right? It is moving with Pe sine theta. If at all you want to hold this electric dipole in this particular position, it is already moving with this value, right? But if at all you want to hold in that particular position, then what you do? You apply a counter torque on that. You develop a counter torque. Instead of moving here, you move another torque here and like this, right? Now this particular torque is used or is implied on this dipole to hold the dipole into that electric field. If there was no counter torque on this acting on this dipole, then this dipole would rotate with this value of torque, right, into this electric field, and hence you require to hold this particular dipole in this electric field position, you require another torque which is exactly equal to this value, which is little more than this particular value. So that instead of moving this particular dipole like this, you just shift it with some distance so that it makes an angle theta now. That is d theta here. Right? Now this torque which is required to hold this particular position, you call it as external torque, which is almost equal to this equation, that is this value, but little more than this torque, right? Say for example you had a torque value of say 5.5, right? Then it is 5.55. Right, a little more, right, considerably little more than the torque, right? The external torque that is used to hold this electric dipole in that particular electric field will be called as external torque. Okay, what you do here is, now the dipole is moving or it is rotating in this direction, clockwise direction, with some particular magnitude of the torque. Now to hold this dipole into this electric field, we introduce another counter torque which is bit greater than the acting torque. That acting torque is in clockwise direction, we introduce another into anti-clockwise direction, right? And we just move a little this dipole to a certain value of d theta, making a small work done, right? What is the small work done? The small work done is equal to, that is torque applied externally to move a value of theta, that is d theta, right? We just move it. We do not move it very greatly. If at all we move it greatly, then kinetic energy comes into picture. We do not want any kinetic energy for this particular electric dipole. We just want to move it very slowly so that the potential energy itself is shifted, right? So if at all, if there was no this torque, that is external torque, that is counter torque, then what happened to this particular electric dipole? It starts rotating into a direction of electric field and align itself in the direction of electric field, making an angle theta is equal to 0 degree, right? If you could remember the very last classes, I always said you the dipole always tries to align itself in the direction of electric field. If there was no counter torque, if there was no torque external that is applied at this particular point, then this torque would rotate anti-clockwise and shift this dipole into this particular direction, making an angle theta is equal to 0 degree at electric field. And hence to hold this electric dipole into this region, a counter torque is introduced which is called as tau external, that is torque external, right, which is little bit greater than the acting torque. Okay, now you substitute the value of this thing. dW is equal to, what is tau external? It is again Pe sine theta, right, d theta. right? P sine theta d theta. Now this is the value, a very small value or the small work done in moving an electric dipole to a region of d theta, right? What if you want to practically accelerate, or what if at all you want to shift the position of the dipole from a region of theta 1 to theta 2, then what you do, you integrate the whole equation here. This is for small elementary value, that is d theta. If at all you want to know the movement from one theta level to the another theta, that is from one angle to the another angle, then you integrate this equation. Integration of dw is w, right? Pe remains constant, electric field is constant here, and the dipole movement is also constant, right? So you take Pe outside, right? Integration of sine theta, right? From which angle to which angle? We are moving a dipole from an angle of theta 1 to theta 2. Then you put theta 1 to theta 2 dot d theta, right? What is integration of sine theta? It is cos theta. It is w is equal to Pe, right, minus cos theta, theta 1 to theta 2, right? Substitute now. W is equal to Pe, upper limit cos theta 2 minus of lower limit cos theta 1. You can write it as W is equal to Pe cos theta 1 minus cos theta 2, right? Now this is the work done, right, in holding electric dipole in a region of electric field, right? Now this work done will be stored as electrostatic potential energy of this particular dipole, and hence it can be written as, say for example, U is equal to Pe cos theta 1 minus cos theta 2. Right? This will be the electrostatic potential energy of electric dipole that is held into electric field. Is this clear up to this point? You please make a note here. I just forgot to tell you. The direction of this dipole movement will be always from negative to positive, and hence it is directed in this direction. Right? I have represented this P in the direction from negative to positive. The dipole movement direction will be always from negative to the positive, right? Did you follow up to this particular point? Now what we do next is, we have a reference point. We will get a reference point. Say for example, we will define, or we will fix a reference point, say theta 1, and with respect to theta 1, wherever it is moving, we consider it as a theta 2, right? Say for example, now the dipole is like this. What if the dipole is placed perpendicular? Say for example, this is electric field line and the dipole is placed like this, such that this theta, that is dipole moment, if at all it is positive q and minus negative q, right? Now this is a dipole which is placed perpendicular to the electric field, making an angle theta. What is this angle theta? It is a dipole moment moving from negative to positive, making an angle theta with electric field. This theta is equal to 90 degree. Say for example, consider theta 1 is equal to 90 degree, right? And then next, to wherever point it shifts the direction or it makes an angle, that angle will be taken as theta 2, making a reference point of theta 1 is equal to 90 degree. Whatever there is a shift in a position of the electric dipole, whether it is shifting to this direction, clockwise direction or anti-clockwise direction, that angle will be considered as theta 2, right? Now what was the formula? We have got U is equal to Pe, right, cos theta 1 minus cos theta 2. This was the formula, right? In this particular formula, this was the that potential energy formula that just now we have derived. In this particular equation, we keep theta 1 as a reference point, as theta 1 is equal to 90 degree. Then what cos 90 will be? Right? Cos 90 will be 0. Then what you are left out with? Pe is equal to cos 90 degree, cos 90 minus cos theta 2, right? Pe will be cos 90 is equal to 0, so you get minus cos theta 2. So therefore, what is the total potential energy of the electric dipole in an electric field? It can be written as minus Pe cos theta 2. Why? Because we have considered the very first angle, that is reference angle, at 90 degree, and hence cos 90 we get 0. We are left out with cos theta 2, the very second angle to whichever direction it is moving. Did you follow? Right? Now this theta 2 can be only written as theta. Why? Because the very first theta is already considered as 0, right? 90 degree, and its value is 0. This theta represents to whichever angle it is moving. So you need not again write it 2 or 3 here. It is just cos theta, right? Now there are 3 conditions when theta is equal to 0 degree, right? When theta is equal to 90 degree, and when theta is equal to 180 degree. There are 3 conditions you need to understand in which the dipole is arranged, right? What do you mean when theta is equal to 0 degree? When theta, initially it is like this, right? A perpendicular. When theta is equal to 0 degree, then it is aligned in a direction of electric field. Then what does it mean? For the very first case, electric field is in this direction, right? Electric field is this direction, and the dipole moment is also in this direction. Theta is equal to 0 degree, right? When theta is equal to 0 degree, what is the amount of the electric potential energy that is being present? Theta 0, then cos 0 will be 1, then U will be equal to minus P into E, right? This is the electrostatic potential energy for the case 1, right? This was the first condition. In the second condition, what we have? Theta is equal to 90 degree. When theta is equal to 90 degree, PE cos 90 degree. Now this will be ruled out, right? Then it is only 0. The potential energy will be equal to 0. And at this particular point, you get position of 0 energy. This is, the first one is position of stable equilibrium. This is position of 0 energy. The third case will be when theta is equal to 180 degree. Then you substitute rho E, that is PE cos 180. Cos 180 is minus 1. Minus into minus plus. So it becomes PE. Right? Now you have maximum amount of the potential energy when theta is aligned in the direction of 180 degree, right? When this particular theta is arranged in the direction of 180 degree, then what does it mean? Now this dipole, this is the electric field, right? Now this, it is aligned like this, minus Q to plus Q, right? Dipole moment is in this direction, electric field is this direction. It is showing 180 degree the angle here, right? At this particular condition, you get maximum amount of the potential energy, that is U is equal to P into E. P stands for dipole moment and E stands for electric field, right? Now there are 3 cases. There are 3 cases that you have to understand. When theta is equal to 0 degree, there is minimum amount of the potential energy. It is called as position of stable equilibrium, right? In the very next condition, that is theta is equal to 90 degree, you get a 0 amount of the potential energy. It is a position of the 0 energy, right? In the third case, the theta is 180 degree, then this is a position of the unstable equilibrium, right? Okay, you can summarize seeing these conditions, right? The whole explanation is brought down to this lines now. If you could understand this, then the entire explanation can be easily remembered, right? In the very first case, theta will be equal to 0. When theta is, what is the theta actually? The angle made between the dipole moment and the electric field, right? If at all the theta is equal to 0, then what does it mean? Theta, that is dipole moment and electric field are in the same direction, and hence theta is equal to 0. This condition is called as stable equilibrium condition, right? In the second, what we have done, theta is equal to 90 degree. This theta, the angle that is made by dipole moment and electric field is 90 degree, right? At this particular condition, what happens? We get 0 values, that is electropotential energy at this particular point when theta is equal to 90 degree is 0, and hence this state is called as 0 energy level, right? In the third point, it was theta is equal to 180 degree. When you substitute theta is equal to 180 degree, you get a positive PE, that is you get a maximum amount of the potential energy, and hence it is called as unstable equilibrium. How the theta is represented? It is 180. This is moving potential, that is the dipole moment is moving in this direction, electric field in this direction, and the theta made between these two will be 180 degree. If you could remember these 3 conditions, the summarized condition, the entire concept remains very clear for you. Is this proper? Right? I hope all the things are very clear to you by this time, right? Okay, this was all about today's class. I hope you have understood the things very properly. The material for this particular chapter will be given into the description box. You please go there, download the notes, you can study, right? You please do share my link with all your friends and families. If at all you have any suggestion, please drop down into the comment box, right? And in the very next class, we'll be dealing with the conductors, dielectric, polarization, and so on other topics, right? So hopefully everything is clear from my end. Keep supporting everyone, and thank you so much.